Welcome to Heat and Materials Lecture 23. In the last lecture I looked at the intermediate stage of solid state sintering and then the final stage of solid state sintering. So this covered areas such as grain growth and densification, and then pore removal and the effects of gas pressure. I then said something about liquid phase sintering and solution precipitation and grain growth. And finally I looked briefly at viscous composite sintering, which applies to the sintering of whitewares. Today I want to say a little bit about viscous glass sintering and then look at asphalt ripening. To start with viscous glass sintering, this applies to glass particles. So in this case, all of the particles can form a liquid. Previously with liquid phase sintering and viscous composite sintering, only limited amounts of liquid were formed. Once we're dealing with viscous glass sintering, all of the particles can transform to a liquid, so this implies that we're dealing with liquids that are at very high viscosity. The initial stage is modelled by a model due to Frenkel and has net formation between two identical spheres by viscous flow. There is no change of shape in that case, and in that particular case it can be shown that the relationship between the diameter of the neck and the radius of the particle raised to the power of 2 is related to 3 times the surface energy times the time divided by 2 times the viscosity and the particle radius. So again, this is fitting the standard form of equations for net formation. Two models that have been developed for other stages of viscous glass sintering are the Mackenzie-Shuttleworth model and the Shearer model. To briefly look at the Mackenzie-Shuttleworth model first, this applies to the final stage when we only have isolated pores. It's assumed because these pores are pores in a viscous liquid that they're spherical and that each pore of radius A is surrounded by a region of influence of radius B. Obviously, because the volume of the sphere is 4/3 pi r cubed, this gives us a relative porosity being equal to A cubed over B cubed. I'm basically just going to show the results of the model. So the first result shown here is for reduced time, which is related to surface energy, the number of pores per unit volume raised to the power of a third divided by the viscosity, is then related to the relative density by this expression shown here. Obviously I've not shown the steps of how that equation is obtained. You can similarly obtain a further equation if there is an applied pressure P, and in this case you introduce a new term B, which is directly proportional to the applied pressure. We obviously get a more complex equation. Again, I'm not going to go through any stages of proof. However, what really matters is the fact that this graph, which shows the relative density as a function of reduced time, if B is 0, which corresponds to the first equation, clearly it takes much longer to reach relative density of 1, i.e. remove all the pores, than it does for higher values of B. Strictly because we are dealing with the final stage, this graph should probably start at a relative density of 0.92. So although I've drawn the curves as if it starts at a relative density of 0, which in fact would be meaningless because even a green body you would expect a relative density of 0.5, really the only physically meaningful part of this graph is the region at the top. But obviously the equations that have been generated can actually apply for any value of the relative density. And that's just a warning that sometimes you can generate equations which apparently give meaningful data, but in practice the underlying physical assumptions mean that a lot of the region is not strictly meaningful. One reason those earlier stages have tended to be looked at is with viscous glass sintering, people have been interested in the sintering of gels to produce sol gel products. And in fact, actually the Mackenzie-Shuttleworth model is very questionable under those circumstances because it depends on closed porosity, whereas a gel starts out as a highly porous material, and Shearer considered gels as being made up of strings of oxide particles which he arranged on a regular cubic grid as shown here, whereas of course in reality the strings of oxide particles will be randomly orientated. But taking a cubic array allows the geometry to be simplified to the point that you can generate an equation relatively easily. And in particular, if you take the cell as having dimension L and the cylindrical strings as having radius A, then you can show that the relative density is given by 3 pi x squared minus 8 times root 2 x cubed, where x is the ratio of the radius of the string to the side of the cell, so I effectively the distance between intersections of the strings. When x equals 0.5, then neighbouring cylinders will touch and the cell will contain a closed pore. In this case, you can take that previous equation to show that the relative density is approximately 0.942, which ties in with the previously given values for when pore closure will occur. So the idea of the Shearer model is that if the relative density is above 0.942, then you use the Mackenzie-Shuttleworth model. If you're below that, then you use the model based on these intersecting strings of oxide particles. The cell dimension can be shown to vary with time as the initial length of the cell side L0 times, so the initial density over the theoretical maximum density raised to the power of a third divided by 3 pi x squared minus 8 root 2 x cubed, or raised to the power of a third. So this is just showing how the length of the side of the cell will vary with time. In common with the Frenkel model, it's assumed that the rate of energy dissipation by viscous flow will equal the rate of energy change due to the reduction in surface area, and working through that gives this overall expression for the time. And actually, despite the differences in the assumed geometry, the Mackenzie-Shuttleworth model and the Shearer model give similar results when they're plotted on the same scale. So this is showing the Shearer model and the Mackenzie-Shuttleworth model plotted together, taking the reduced time before 100% density. So effectively I plotted it on a negative scale here, taking my endpoint as being the time t equals 0. That's easier to enable a comparison of the two models. Obviously they're identical in the region where you've assumed the Mackenzie-Shuttleworth model because you've got closed porosity. Below that, the shapes of the curves are not identical and clearly come down to this axis at a different place, but they're surprisingly similar. This graph actually shows the variation of relative density with reduced time for some real data compared to the Shearer model, and you can see there are generally good agreement. Note the relative density does start in this case at very low values because we are dealing with gels which are much lower density than conventional green bodies.